Okay, so with the exam on Friday, today we're just going to be reviewing by going through some of the problems from the exam 2 review that I posted online on Canvas a week ago. And so I haven't written the exam yet. I've kind of like thought about it a little bit in terms of like what it's going to consist of. You should be thinking that we're covering section 7.3 to 7.7, then sections 8.1 to 8.3. If you ignore section 7.6, which was just like integration review, there's 7 sections that are covered, right? So there's 4 sections here, and then there's 3 sections here. And so you should be thinking there's probably gonna be like 7 problems on the exam. There's 1 problem that represents like a problem from one of these sections. So there's gonna be like 1 problem from section 7.3, 1 from 7.4, 1 from 7.5, and then 1 from 7.7, and then 1 problem for each section from chapter 8 as well. So there's going to be 7 problems, 1 problem representing each of these sections that we've covered. You should be thinking, like the problems that are going to take the most amount of time are going to be the trig substitution problem and the partial fraction problem. It isn't really, like you don't want to be spending like 30 minutes on those 2 problems. So like you should know how to do those problems, but you should also kind of know how to do them in a way that's like pretty quick as well. You don't want to be spending like those problems can take a long time. You don't want to spend like more than half the amount of class just on the partial fraction and trig sub problem. So you should have like a decent amount of practice with those concepts before the exam, I would say. I'm not going to choose a problem or problems from those 2 sections that are like really difficult. But I'll choose one that's kind of like of middle difficulty is what I would say. So you need to make sure you can do those problems in a way that's somewhat, maybe not like super fast, but like relatively quickly. And then the other problems, like if you do like the partial fraction problem and the trig sub problem in like 20 minutes, that gives you 30 minutes for the other 5 problems, which is 6 minutes per problem. So it's like a good way to kind of like pace yourself, I suppose. Okay, so I don't really have much else to say about the exam yet. I haven't written it. It'll be 7 problems, as I just said. Okay, so here's the exam review. You can find this online, and I'll post the solutions to the exam review as well as the group works since the last exam on Canvas after class. So around like noon today, I'll have them posted on Canvas, and I'll send out an email as well, so you'll all remember to look at it. Okay, so without further ado, I guess I'll just open the floor to any questions that people have about the review. Are there any particular problems people want me to go over before I just start choosing some? Oh yeah, Rita. 4. Okay. Yeah, so for problem number 4, it wants you to use comparison to show that the following integral ends up converging. I'm not really sure if I'm going to include the comparison test or not, but I mean, it could show up. Maybe it'll show up, maybe it won't. I don't know yet. And so this is the integral that's given to us. So this is problem 4. We have the following integral. We have the integral from 1 to infinity of 1 minus sine of x over x squared dx. And we're asking ourselves the question, does it converge? Right? One of the bounds of integration is given by infinity. So there's a chance that this goes to infinity, or like it's not a finite number, which means that it would diverge. Let me just make sure I'm recording. Okay. And so if you wanted to compute this integral, like this is a challenging integral to compute just using like really any technique directly. And so you want to compare it to another integral that's easy to compute. And I guess like the main hint, I mean, I'm telling you to use comparison already, but even if I didn't tell you to use comparison, you should be observing that baked inside of this function, there's another function we already know about that converges, that function being 1 over x squared, right? We already know that 1 over x squared converges by the p-test from section 7.7. I think we also just did an example or like computation of what it ends up being. So we want to somehow compare this to 1 over x squared or something over x squared. It doesn't matter what's in the numerator pretty much. And so this is the main idea. So we want to use the fact that sine of x has a really easy bound to work with. We know sine of x is bounded between -1 and 1. So we know -1 is always less than or equal to sine of x, and this is always less than or equal to 1, you can just think about the graph for sine, right? The graph of sine looks something like this, where this is 1 and this is -1. So it's always bounded by 1 and bounded below by -1. What this tells you is it's going to give you a restriction on how high this numerator can get, right? The largest this numerator can get is when we have 1 minus -1, right? Or really like 1 plus 1. So a sine's bounded between -1 and 1. This implies that 1 minus sine of x is always going to be less than or equal to 2. And so because we know that 1 minus sine of x is always less than or equal to 2, we can then just apply it to this whole function here. Like 1 minus sine of x is less than 2, and then we're dividing by x squared. So this implies that we have 1 minus sine of x over x squared is less than or equal to 2 over x squared. And now it's just a matter of showing whether or not this integral or this function converges within this integral. And so this implies that we have that the integral of 1 minus sine of x over x squared from 1 to infinity, this is going to be less than or equal, let's include the dx, this is less than or equal to the integral from 1 to infinity of 2 over x squared dx. And so because the power of x in the denominator is greater than 1, we already know that this is going to end up converging. So, I mean, if you want to, you can compute this like integral and show that it ends up being a finite number. But we already know from a theorem that like this is going to end up converging. So as the power of x in the denominator is greater than 1, we know that this integral from 1 to infinity of 2 over x squared dx is going to converge. And because this integral converges, it must mean that this integral converges as well, because this integral is less than or equal to this one right here. So this integral from 1 to infinity of 1 minus sine of x over x squared dx has to converge as well. So again, I mean, we didn't do that much with the comparison test, so I don't know if they'll really show up on the exam, but I don't know, I might choose to put one on here. I'm not really sure yet. But anyways, are there any questions about how to do this problem or like the logic in it? Yeah, question. Yeah. Any other questions about 4 before we move on? Okay. Yeah, and then the main point was just seeing that there's like this 1 minus x squared. So changing the numerator so it incorporates like something of like something over x squared, because we know how to work with this via the c-test. Okay, so the next one is problem 6. Oh yeah, I think this one's a homework problem as well next week. Okay, so for problem 6, we have the following. Let me just pull it up so I can write it out. Oh yeah, so 6, this is probably, maybe not the function itself, but for the probability function or probability problem, it's probably going to be something of this nature. So for problem 6, it wants you to find a constant c. Such that we have that the probability of x given by c of e to the minus x times e to the minus e to the minus x is a probability density function. And then from there, it also wants you to compute the following. This is kind of the like this part's not really that interesting. It's just computing an integral. So like it wants you to compute the probability that x is between -4 and 4. I'll kind of write this out in a single line after I'm done with this part right here. So if we want to find a constant c such that this ends up being a probability density function, we have to, wait, do I not give, oh, I forgot to include the domain. So we're on the interval from minus infinity to infinity. Right, so we're going to take the integral from minus infinity to infinity of this function right here, and then we're going to set it equal to 1, and then from there, we'll solve for c. Okay, so what do we end up having? So before even computing the definite integral, let's just see what the antiderivative of p ends up being. So let's just take the antiderivative of c times e to the minus x times e to the minus e to the minus x dx. If you want to solve this integral, you're just going to use u substitution, right? So we'll just let u be equal to e to the minus x. So that tells you that du is going to be equal to minus e to the minus x dx. And so you have the following. I'm going to pull the c outside of the integral. So this is going to be equal to c times the integral. So we have a e to the minus x times dx. That's kind of like our du, except we just have a minus sign in front. So I'm going to bring out the minus sign in front of the integral. So this is really the same thing as having minus c. Then we're going to have a du. And then we let u be equal to e to the minus x, and we have an e to the minus e to the minus x. So this is really just going to be e to the minus u. And so if you integrate this, this just gives you c times e to the minus u. And then if you plug back in for u, this will give you c times e to the minus e to the minus x. Okay, so this is the antiderivative of the probability function that they give you in the beginning. And so what we want to do with this is we want to now consider the definite integral. We're going from minus infinity to infinity, and we're going to set this equal to 1, what we end up getting here. And so this is going to end up implying that we have that this integral from minus infinity to infinity of c times e to the minus x times e to the minus e to the minus x dx. We're going to set this equal to 1 because we want this to be a probability density function. And so this is going to end up being equal to the following. This is going to end up being equal to, I feel like I don't like that I included this problem, because now I have to have like, you have to have kind of r's that correspond to both like minus infinity or infinity, or you can use a single r and you can write things out as like plus and minus r if you want. I'm just going to write out 2 limits. So I haven't seen this notation before, but I don't want to write 2 limits out. So I'm going to say we're going to have 2 limits. The limit is r1 goes to infinity, and the limit of r2 as it goes to minus infinity, corresponding to these 2 limits of integration that we have. And then we know that the antiderivative of this function here is equal to c times e to the minus e to the minus x. So this is going to be times c times e to the minus e to the minus x. And so the bounds of integration are going to be this r2 that's substituted in for minus infinity, and then it's r1 that's substituted in for infinity. And again, you could make this easier for yourself. Like you can just write this as the limit as r goes to infinity, and then just write like minus r here and then r here if you want. But I don't know, maybe this makes it more clear as to what I'm doing. Like we have a minus infinity, that's like this thing here, and we have an infinity, which is this thing here. Okay, and so now it's just a matter of plugging in r1 and r2 and then seeing what happens when you perform the limit. And so this is really going to be the same thing as the following. So this is going to end up being the limits as r1 goes to infinity and r2 goes to minus infinity of what you get when you plug in r1 and r2 into this. And so you can write this out in the following way. I'm also going, let's just take out the c from the limit. So this is going to be e to the minus e to the minus r1 minus e to the minus e to the minus r2. And so this looks kind of rough right now, but you can rewrite this in a way that makes it a little bit easier to think about, like what's happening with the limit here. because like ultimately we're interested in finding this limit or these limits. So this is going to be c times these limits as r1 goes to infinity, r2 goes to minus infinity. So instead of writing e to the minus r1, you can also write this as e to the minus 1 over e to the r1. And then this is going to be minus e to the minus 1 over e to the r2, like this, because we have like a negative exponent, right? And so you should be thinking that as r1 goes to infinity, this fraction is going to go to 0. And if you have e to the 0, this is going to be equal to 1. So this is going to be c times 1. And as this is going to minus infinity, this e is going to end up being going, or as this goes to minus infinity, like we really just have like e to the minus x. So this is going to end up going to 0. So this is going to be minus 0, which ends up being c. And so what we end up finding is we ended up finding that 1 ends up just being equal to c. So this implies that c has to be equal to 1. Okay, yeah, so I think the hard part's actually probably just like computing the limit in the first place, or like going from here, thinking of like recontextualizing it so you think about it in terms of like e to some fraction, and then interpreting what's happening. With these, just knowing the fact that the exponential function kind of looks like this, right? So knowing the shape of the exponential function helps, because this is what e to the x looks like, right? And so as r2 goes to minus infinity, we're kind of going like this way. Here, as this one goes to infinity, we're approaching 0. Okay. Any questions? And then there's one other part. The other part isn't really that interesting. I don't think I'm going to ask this part on the exam. And if you want to do this part, all you do is just compute this or evaluate this integral from like -4 to 4, pretty much, right? So this was that's like this part right here. So you'll just evaluate this antiderivative going from x is equal to -4 to 4, and that would be your answer. You can leave it like that on the exam. Okay, any questions about 6? Yeah, and I'll say this one's a little bit harder than what would be on the exam as well. Like I'm not going to do like double infinities, right? So it'll be a little bit easier than this on the exam. In general, that's true for most of the problems on the review. Like the problems on the review are harder on average than what you'll find on the exam. But it's like taking the weights off for the exam, you know? Like if you can do the review, like you should be able to do the exam pretty easily. Okay. What other problems do people want me to go through? Rita and then 9. Okay, yeah, we can do 9b. So I think 9b wants you to do an arc length. Yeah, write it down. So for 9b, wants you to do the following. So 9b wants you to compute the arc length of the following function. So we have, I'll just say f of x is equal to the natural log of cosine of x. And then we're integrating from 0 to pi over 4. And so for this one, it helps to remember what the arc length formula is given by. So we have that arc length in general is given by the following formula. So arc length, this is going to be equal to the integral from 0 to pi over 4 of the square root of 1 plus the derivative squared dx. So this is a general equation for the arc length. I guess I put in like the parameters given to us, but what this is saying is we want to find the derivative of f of x. We want to square it, then we'll add 1 to it and take the square root, and then we'll find the integral of this. And so like the other arc length problems we found, the main challenge is going to be finding a way to cancel out with the square root. So that way the integral doesn't get too bad when computing the arc length. And so a lot of the work is just done in the beginning. So we have f of x, this is equal to the natural log cosine of x. First, we'll take the derivative of this function. So we have f prime of x. This is going to be equal to 1 over cosine of x times minus sine of x. And so this is really equal. So we have sine of x over cosine of x. So this is really minus tangent. So this is really equal to minus tangent of x. And then from there, we want to consider 1, or maybe I should use like a word instead of an arrow. And so we ultimately want to find 1 plus the derivative squared. And we know the derivative is minus tangent of x. So this implies that we have 1 plus f prime of x squared. This is the same thing as 1 plus tangent squared of x. For where? Oh, we're taking minus tangent and then we're squaring it. Oh, there should be a square here. Like we're taking minus tangent and then we're squaring it, so it becomes like 1 plus tangent squared. And so the main trick here that's going to make it so this ends up going away is like we're going to have a 1 plus tangent squared of x, but we can rewrite 1 plus tangent squared as just being equal to secant squared. Right? This is just, this is an identity you should know. It's just the Pythagorean identity. So we have like sine squared of x plus cosine squared of x is equal to 1. If we divide everything by cosine squared, this tells us that we have tangent squared plus 1 is equal to secant squared, right? We've derived this a couple of times in class at this point. So you should know this identity. It's just a corollary from the Pythagorean identity. And so this is telling us that 1 plus the derivative squared is just equal to secant squared of x. And now we can compute the arc length, right? We know 1 plus the derivative squared, so we can just plug it in to this integral here. So we have that the arc length, this is equal to the integral from 0 to pi over 4 of the square root of 1 plus the derivative of x squared dx. And so this is going to be equal. So now we just write in what we just found out. So this is pi over 4. This is going to be the square root of secant squared of x dx. And so this is how we cancel out with the square root, right? We have a secant squared, we have a square root. Those things cancel out with one another. So this is equal to the integral from 0 to pi over 4 of secant of x dx. And then this is an integral we've seen a couple of times. This is equal to the natural log of secant of x plus tangent of x. And then we're evaluating from 0 to pi over 4. And so, you can leave your answer like this on the exam. The only time you have to expand this answer out is when you're doing improper integrals, like when you have like a limit, you want to show whether or not something converges, you actually have to go through. But for arc length, you can leave your answer like this. But if you plug the numbers in, you should end up getting that this is going to be the natural log of 2, or the square root of 2 plus 1. Yeah, so you kind of have to know your your trig identity. Otherwise, like if you kind of leave things as 1 plus tangent squared, it's kind of difficult to determine like how you would compute the integral. But knowing it's equal to secant squared makes it so things cancel out nicely. Okay, any questions about 9b? Okay, what next? What other problems? 1c. Yeah, I think this should be a trig subproblem. Okay. So 1c to do the following integral. So for 1c, we have the integral of 1 over 9x plus 4 squared dx. And once you define what this integral ends up being equal to, And so I guess the first thing we need to do, oh, there should be 9x squared, right? Wait, does it? Okay, it says 9x squared. I just wrote it down incorrectly. Okay, yeah, there. Okay, they match. Okay, so we want to find this integral. And so if you ignore the 9, we have something in the form of like 1 over x squared plus 4. And then I guess we're squaring it. So even though we have a square, we don't have like a square root, you can still use trig substitution here. Like usually we'd use trig sub when we have a square root or like a 3/2 power. But really it applies anytime you have something of the form of like n over 2. In this case, it's really like 4 over 2. So you have like a square. So you want to use trig sub pretty much whenever you have like a square plus some constant or minus a constant or so on and so forth. And so if we want to use trig substitution, we want our x squared to be on its own. We don't want this 9 being multiplied by it. So before even determining like what x is going to be equal to, we're going to factor out this 9. So this is really going to be 1 over 9 times x squared plus 4 over 9. And then all of this is going to be squared. So we can rewrite this really in the following way. So we have like a 9 squared here. You can pull it outside. Like you can write this as like 81 or 1 over 81. So this is really going to be 1 over 81 times this integral from, or integral of 1 over x squared plus 4 over 9 squared like this dx. And once your integral is in this form, it's more easy to see what your x is going to end up being equal to. So we don't have a coefficient with x, so that's good. And then we have something in the form of like x squared plus another number. So we know we're going to use tangent theta. Is this going to be a matter of determining what we're multiplying to tangent? So that's where this 4 over 9 comes from. So we should be thinking that a squared is equal to 4 over 9. If you take the square root of both sides, that's going to tell you that a is equal to 2 over 3. And so once we know what a is equal to, we can determine that x is going to be equal to 2 over 3 times tangent theta. If you take the derivative, you have dx is going to be 2 over 3 times secant squared theta d theta. And then we just make a bunch of substitutions, right? So we know what x is equal to, we know what dx is equal to. And so now we just plug in a bunch of things. I'm gonna separate this out. So this is what x is equal to. This is what dx is equal to. And so continuing by making a substitution, we really have this as 1 over 81 times this integral. So dx was equal to 2 over 3 secant squared theta. So I'm just going to write this like 2 over 3 secant squared theta d theta. Or I don't like writing d theta in the numerator, so I'll leave it like this. And then in the denominator, we're going to have a 4 over 9 tangent squared theta, and that's going to be plus 4 over 9, and then all of this is squared. And then this is going to be d theta. And so from here, there's kind of like a lot of terms messing around. So we have like a 2 over 3 times a 1 over 81. And then we also have like a 4 over 9 we can factor out, and then you square that. So you have like a 16 over 81. So there's kind of like a lot that can go on with these. Like you really have like a 1 over 81 multiplied by 2 over 3. And then you can factor out like this, like 4 over 9 squared in the denominator. So this is like 1 over 4 over 9 squared, which is really 81 over 16. I'll show you what this like multiplies into after I'm done writing out this next step. So it gets a little bit messy. In the numerator, you still have the secant squared of x. And then in the denominator, you have just a tangent squared theta plus 1 squared d theta. Right, and so if you multiply all these terms out, you should end up getting this is equal to 1 over 24. And then here we have secant squared theta in the numerator. This term here, this tangent squared plus 1, just as we saw in the previous example we worked through, this is equal to secant squared theta. And then we're squaring it, so we really have a secant to the 4th power. d theta. So these terms cancel out, or at least like two powers in the denominator end up canceling out. So you get 1 over secant squared, which you can then just see as being equal to cosine squared. So I'll write it out like this is 1 over 24 times the integral of 1 over secant squared theta d theta. So this is 1 over 24 times the integral of cosine squared d theta. Yeah, so for this one, I mean, you have to use like you can either do like the double angle formulas or half angle formulas, or you can use like the reduction formula. On the exam, you're not going to need to use the reduction formula, but let's just write this out anyways. So this ends up being equal. So by the reduction formula, this is 1 over 24 times 1/2 cosine theta times sine theta, and then this is plus 1/2 of theta, and then you have a plus c. And so all that's left at this point is your final answer has to be in terms of x instead of in terms of theta. And so you have to draw this triangle out. So we have this triangle, and to determine the side lengths of a triangle, we always go back to the original way in which we related x and theta with one another. So we always had that x was equal to 2 over 3 times tangent theta. And so this tells us that 3x over 2 is equal to tangent theta. And you should remember that tangent theta is opposite over adjacent. So this is going to be 3x over 2. And then in the numerator, or by the hypotenuse by Pythagorean's theorem, this is going to be 9x to the 4th power plus 4. Right, so it's 3x squared. Oh, I don't know, I wrote a 4th power. 9x squared plus 4. And you can see that's kind of what we originally had in the denominator. It's just 9x squared plus 4. Okay, and so now we can determine what sine and cosine end up being equal to. So this is 1 over 24. Let me, I mean, both things are being multiplied by 1/2. So let's make this 1 over 48. We have cosine is adjacent over hypotenuse. So this is 2 over the square root 9x squared plus 4 times sine. Sine is opposite over hypotenuse. So this is 3x over the square root 9x squared plus 4. So you can multiply these things together and get rid of the square root. And that's going to be plus 1/2 of theta. So we found that tangent theta is equal to 3x over 2. If you want to solve for theta, just apply arctangent to both sides. So we have inverse tangent of 3x over 2 is equal to theta. And so this is going, oh, I factored out the 1/2, so this shouldn't be here anymore. So this will be plus inverse tangent of 3x over 2. Okay, so you can simplify more if you want, but just leave your answer like this. Like from here, it's just kind of uninteresting. Yeah, so again, like these trig subproblems are kind of monstrous. They can take a lot. I'm going to try and find it so it's like not going to be this long. And like, I'm not going to make you use the reduction formula on the exam. So you don't have to worry about like the integral of cosine squared or anything like that. But it's good to know just in general. Maybe in like Calc 3 it will show up. Okay, any questions about 1C? Okay, let me look at, okay, what other problems do people want me to go through? Yeah. Yeah, 11. Is there like a particular one of these two from 11, or? I think part B is probably a little bit more interesting. Part A isn't too bad. Like you just apply the formula that's given. Okay, so let's just do 11. Let's do 11B. 11A isn't too bad. So for 11B, it wants us to do the following. So it wants us to compute the surface area, revolution about the x-axis, or the following. So we have y is equal to the square root of x. And then we're going over the interval from 0 to 1. And so in general, this is the equation that you need to know for computing the surface area. It's kind of like the arc length formula, except you have like a 2 pi. You have like an area or like a circumference that's kind of like concatenated with it. So this is like the surface area is given by 2 pi times this integral from 0 to 1 of whatever your y. Maybe instead of y, let's write f of x. This is like f of x. I mean, it doesn't really make a difference, but I like writing f of x instead of y inside of the integral. This will be 1 plus the derivative squared. Right, so this part is really just like the arc length, but then you also have like this f of x that you're multiplying it by. And so for this particular example, we have f of x is the square root of x. So this is 2 pi times the integral from 0 to 1 of the square root of x. And then we have 1 plus f prime of x squared dx. And so let's see what happens with f prime of x here. So we want to take the derivative of the square root of x. So the derivative of the square root, so f of x, this is equal to the square root of x. By the power rule, you have f prime of x. This ends up being equal to 1 over 2 times the square root of x, right? You can think of this as being like x to the 1/2. So if you take the derivative of this thing, you end up getting this as 1/2 of x to the minus 1/2, which is exactly what I have written here, just writing it out in terms of the square root. And so if you take the square, so once we determine, I'm really just repeating the process we did for the arc length formula, right? Like this is really the same thing as doing like, we're not the same thing. Like we're doing 1 plus the derivative squared. So what happens if we have like 1 plus f prime of x squared? This would be equal to 1 plus 1 over 4x. And then if you wanted to, you can kind of combine this into a single fraction via common denominators. So you can multiply 1 by 4x over 4x. And so this is equal to 4x plus 1 over 4x. And so let's see what happens. So this is 1 plus the derivative squared. So we can just plug this term in to what we have inside of the square root here. And then we'll just see what happens pretty much. So this is equal to 2 pi times the integral from 0 to 1 of the square root of x. This is times the square root. So 1 plus the derivative squared, we found to be 4x plus 1 over 4x. So it doesn't really do a lot in terms of canceling out the square root, but it does have another role in the sense that we can factor out this square root, or we can bring this like square root of 4x out of like the square root here. So like what I'm saying is the following. So this is like 2 pi times the integral from 0 to 1. This is the same thing as doing the square root of x multiplied by 1 over the square root of 4x. And then this is multiplied by the square root of 4x plus 1 dx. Right, so I'm just rewriting this square root as the following product, or thinking about taking out like this 1 over 4x like outside of this larger square root. The reason why I do that is we have like this is really going to tell us that this is equal the 2 pi. Like this is going to cancel out with the square root of x. That's the main point. So this is going to be 2 pi times the integral from 0 to 1. So this is really the same thing. If you multiply these two things together, you'll have a square root of x in the numerator. The square root of 4 is just equal to 2. So this is going to be over 2. And then we have like a square root of x. So this is the square root of x multiplied by the square root of 4x plus 1 dx. So the main point is we have the square root of x cancels out with the square root of x. And then this 2 cancels out with this 2 right here. And so you're going to be left with the following integral. This is going to be pi times the integral from 0 to 1 of the square root of 4x plus 1 dx. And then once you're here, it's a pretty straightforward just u substitution, right? So if you wanted to use u substitution, you can just let u be equal to 4x plus 1. Du is then just equal to 4 dx. You can divide both sides by 4 to get 1 over 4 du. is equal to dx. And so this is going to end up being equal to pi over 4 times this integral. So 4x plus 1 was equal to u. So we really just have the square root of u, which you can write as u to the 1/2 power. If you want, you can kind of ignore the limits of integration after you're done finding the antiderivative of this, and then you can do it in terms of x. I like plugging things in. So like if you plug in x is equal to 0 into this, you end up getting 1. If you plug in x is equal to 1, you end up getting 5. So this goes from 1 to 5 with respect to u. And then from here, it's just a matter of integrating things out. So this is going to be equal to pi over 4 times 2 over 3 times the times u to the 3/2 power. It's evaluated from 1 to 5. So you can leave your answer like this. If you plug in 5 and 1, this would be equal to, you end up getting the following. So you'll multiply things out. You end up getting this is pi over 6 times 5 times the square root of 5 minus 1, like this. So on the exam, considering like time, you kind of want to leave your answer like this instead of plugging numbers in, right? Yeah, so the interesting part, again, is this simplifying things algebraically. So that way you eventually cancel things out till you eventually get an integral that's easy to compute. So like most of these, like the surface area and the arc length problems, like the challenging part is really just the algebra, I would say. Okay, any questions about this example? Yeah.
How did you get 5?
Oh, like this 5?
Yeah.
Yeah, I mean, so like how I do things is like we went from an integral in terms of x to an integral in terms of u. So that means instead of having these terms in terms of x, you need to translate things in terms of u instead. So I plugged in x is equal to 0 to get 4 times 0 plus 1. That gives you this 1. And if you plug in x is equal to 1, you get 4 plus 1, which is this 5. You don't have to do things this way. You can find the antiderivative with respect to u and then translate back in terms of x, and then you can use the original limits of integration. And you should get the exact same number at the end of the day. So it's up to you. I just like doing it this way. Like I like translating in terms of x and in terms of u. Okay, I have time to go through one more problem. Is there another problem that people want me to go through? Yeah. 8. I mean, I did 8 in class before, so there's already like a video lecture of me going through problem 8. So I'd say like it's probably a good one to skip because you already see like an explanation for it. So I'm probably gonna skip that one. Plus it's long and I don't want to do it. Okay, so is there like another problem? Probably like just keep on. Yeah, so I did this, like if you look at the section 8.1 video lecture, there'll be an explanation of me going through this problem. 12. Is there like a particular part of 12 or like both? You want me to do like both the equilateral triangle and like the slanted rectangle? Or... Okay, yeah, so I'll start off with the equilateral triangle. So for the, yeah, so there's like 2 faces to this. There's like this equilateral triangle I want you to find the fluid force applied to. And then there's also this slanted rectangle as well. And so depending on what surface you're looking at, the area is going to be different. So you're going to have different integrals. And so we'll first look at the triangle. And then if we have time, we'll do the slanted rectangle as well. And so if we want to do the triangle, like ultimately what we want to do is we want to be using like similar triangles to determine this. And so there's 2 variables you should be aware of. There's kind of like this depth, or how am I doing this? So there's kind of like this depth, which is given by y. So when doing fluid force, you should always associate y with your depth. And then because the width of the triangle is changing over time, we need to account for that by looking at some width function given by f of y. And so this is f of y. And then you should be thinking like this 5 and this like f of y kind of relate in that they're both like widths of a triangle. And then we have like this y should correspond to whatever the height of this triangle ends up being. So it's drawn slanted, so it's a little bit weird. So like we have like this h right here. On the exam, I'll just tell you what h is equal to. And I kind of want to derive how you find the height of an equilateral triangle. You just use the Pythagorean theorem, but in the interest of time, I'll just write it out. So like the height of an equilateral triangle is always given by the following. So it's given by the square root of 3 over 2 multiplied by the side length. Right, it's an equilateral triangle, so all the side lengths are the exact same. So in this case, we have the side length is given by 5. So this is equal to 5 times the square root of 3 over 2. I guess on the exam, because I haven't shown you how to derive this equation, if there is an equilateral triangle, I'll just tell you how to find the height, or I'll just tell you what the height ends up being. And so by similar triangles, we have the following. So we have like this larger equilateral triangle, and then inside of it, we have like this smaller triangle with width given by f of y, and then the height's given by y. So we can use similar triangles. So by similar triangles, we have the following. And so we have at the, let's say like 5 over, so like 5 is kind of like the base. This is going to be over the height. So this is 5 times the square root of 3 over 2. This is going to be equal to f of y over y. Maybe I should write it out like this. So this is kind of like side length over height. And so 5 is the side length of the larger triangle. F of y is the side length of the smaller triangle. So that's why they're on the numerator here. And then we have the height of the larger triangle. This is 5 times the square root of 3 over 2. The height of the smaller triangle is given by y. And so we want to solve for f of y, right? Like that's the main point. Like the ultimate integral we're going to be looking at has the following form. So like the force is equal to rho times g times like this integral from 3 to 3 plus 5 square root of 3 over 2. I'll talk more about that later, of y times f of y dy. And so we know what, I mean, y is just the variable itself, but we don't know what f of y is. So that's why we're doing these similar triangles, is to find a way in which we can write f of y in terms of y. And so if you solve for f of y, you end up getting the following. So you end up, like, you multiply both sides by 5 or by y. The 5s cancel out with one another. And then like square root of 3 over 2 is really like 2 over the square root of 3 multiplied by y. So this ends up being 2 over the square root of 3 times y is equal to f of y. And so this tells you that the integral is going to be the following. So this is going to be rho times g times this integral. So the reason why I have 3 to 3 plus this thing right here is it tells you in the beginning that the top of this triangle is 3 meters down. So like we're starting our depth at 3, and then the height of this triangle was given by 5 times the square root of 3 over 2. So to get the overall depth here at the bottom, it's going to be 3 plus the height of the triangle. So that's why I'm doing like this 3 plus the height right here. You can also do something like, instead of writing y, you can write this as y plus 3. You just go from like 0 to like the height of the triangle. But I think this is more intuitive, and it lines up with how we are doing things in class. And so this is 3. This is 3 plus 5 times the square root of 3 over 2. And so this is going to be y times 2 over the square root of 3 times y dy. And on the exam, I'll just ask you to set up the integral. I mean, computing this integral, you just get like a y squared. So you get like 1 over 3y cubed multiplied by some numbers. So this ends up being, so this row here, it's density. The density of water is given by 10 cubed. I would give you that on the exam. You don't have to memorize that. Gravity is 9.8. Then you have like 2 square root of 3. They have this integral with these bounds. And so you just have y times y remaining. So this is like y squared dy. So, I mean, you can leave your answer like this if you want. So I'll just ask you to set up the integral on the exam. Like computing, it's not really interesting. Okay, so I don't have time to do the slanted rectangle, but I'll post the solutions to this in a couple of hours and you can see how it's done. It's kind of similar to the dam problem, like the Yangtze Dam problem we did on Monday. Okay, any questions? Okay, so I'll be posting the solutions to the group work as well as the recording of this in a couple of hours. If you have any other questions, I'll be in my office until about like 1 o'clock today. So from like 11 to 1. And if you have any other questions, you can email me as well.